Okay, my name is Sunny Arora and I'm assistant professor in AKGEC College, Department of Computer Science. So today I'm going to take this topic, parallel processing and introduction of pipelining. Parallel processing is basically to provide the simultaneously data processing tasks for purpose of increasing the computational speed of computer systems. So why do we do parallel processing? Basically, we want an improved throughput. We want a better throughput. Therefore, we require this simultaneously data processing task. Okay, so therefore we require this parallel processing. So in parallel processing, we basically need extra hardware that we are going to utilize in a best manner so that we can have a better throughput, better computational speed. So for example, while an instruction is being executed in ALU, the next instruction can be read from the memory. So parallelly, two tasks are being done. One, the instruction is being read from the memory, instruction is being fetched from the memory, and secondly, the next instruction is executing at the same time. So parallelly, two tasks are being done. One, the instruction is executing and another instruction is being fetched at the same time. So that is one of the smallest example of parallel processing. The system may have two or more ALUs and be able to execute two or more instructions at the same time. Another example is that we can have in a system like two or more ALUs. That means two or more arithmetic logic units. So parallelly, those both units can work together, and they can both execute the two or more instruction at the same time. So that is another example of parallel processing. Next is the purpose of parallel processing is to speed up the computer processing capability to increase throughput, that I have already discussed. And the last point is the amount of hardware increases with parallel processing. So once we add additional hardware in our system, so that definitely increases the cost. Okay, so that increases the cost because we are installing additional hardware in the system to get the parallel processing. Okay, that is our last point. So next is parallel processing can be viewed from various levels of complexity. So one is the lower level and another is the higher level. Okay, so in lower level, what we have an example which I have highlighted over here. Shift registers operate in serial fashion, one bit at a time. So what does that mean? Like we have already studied shift registers, or we can say we have already studied the shift operations, such as in shift left operation, arithmetic shift left, shift right, and arithmetic shift right. So every bit is shifted one at a time sequentially. Okay, so that is not the parallel processing, because it is a sequential processing, because every bit is being shifted one at a time. Every bit is shifted sequentially. And second is when we see a register, and we have seen how do we load registers in the topic common bus system. We have come across, we have seen so many registers present there, such as input register, output register, program counter, accumulator, temporary register, instruction register, and so on. So there we have understood that one register can be loaded parallelly. So there are some load pins, and through those pins we load bits parallelly in a register. So that is another example of lower level of complexity in parallel processing, right? So next is higher level. In higher level, we can have a multiplicity of functional units in the system. So what does that mean? For example, see this figure. Here we see that we have multiple circuits, multiple functional units in our system, such as adder, subtractor, integer multiplicity, logic unit, shift unit, incrementer, floating point add, addition and subtraction unit, and for similarly floating point multiply unit and divide unit. Okay, so we can have different kinds of functional units present in our system to improve parallel processing. But again, this is a drawback, because this will add complexity. How? Because of circuitry, a lot of circuitry, that could be a mess up. and secondly, it will increase the cost. You have to buy multiple functional units to do these operations, so therefore you have to do you have to spend extra for the extra hardware. Okay, so that will increase cost for parallel processing by installing these multiple functional units in our system. Okay, next is how do we classify parallel processing? There is a very important concept, that is Flint's classification. Okay, so Flint has basically classified this parallel processing into 4 categories, right? The first one is that is called as SISD, that is single instruction stream, single data stream. So first of all, to understand all these 4 categories like SISD, SIMD, MISD and MIMD, we need to understand what is an instruction stream and what is a data stream. Okay, instruction stream is basically like we already know that a program is a set of instructions. So we basically fetch instruction one by one through the help of the program counter. Program counters gives you the address of the next instruction to be executed, which gets updated parallelly while the instruction is in progress in its execution, right? So see this red highlighted part, the sequence of instruction read from memory constitutes an instruction stream. That means the sequence of instructions which are present in a memory, that is called as an instruction stream. Okay, one instruction after the another and so on and so forth. So that is instruction stream, right? So thereafter we have data stream. Now what is a data stream? The operations performed on the data in the processor consist of a data stream. Okay, let's take an example. Like in instruction, we know that there is an opcode and addressing mode and the mode bit, right? In an instruction format, we have 3 things. What? Opcode and a mode bit and addressing mode. Why is the addressing mode there? That we have already studied, to get the operand. Okay, to get the effective address of the operand or the operand. Okay, so basically opcode gives you the micro operation that is supposed to be applied on the data. Okay, on the operand basically. So data stream is it is kind of operations that we apply on operands. It is a kind of you can say it is a kind of data that we are working upon. So that is basically called as a data stream. All right, so we have an instruction stream and data stream. So on the basis of these data streams and instruction streams, the Flint has classified the parallel processing, right? So first one is your single instruction stream, single data stream. Second is your single instruction stream and multiple data stream. And third is multiple instruction stream and single data stream. And the last one is multiple instruction stream and multiple data stream, right? So let's come to the first part, that is single instruction, single data stream. Okay, that represents an organization of single computer containing a control unit, a processor unit and a memory unit, right? So SISD basically has one control unit, that is single control unit, single processor and a memory unit, a single memory unit, right? So basically one task, single task is being processed by the single unit in this. Okay, in the second, that is SIMD. SIMD is single instruction stream, multiple data streams. Okay, here many processing units are present. Okay, many processing unit means it can have multiple ALUs, okay, or multiple control units likewise. But many processing units under the supervision of common control units. It's like we have a common control unit which is controlling the multiple processing units. So there can be many processors which are working on the same instruction. Okay, so all processors receive the same instruction from the control unit but operate on different items of the data, right? So we have to understand here that there are multiple processors, such as we have learned this term multiprocessing, which means there are multiple processors present in a system. Okay, so but those multiple processors are working on the same instruction from the control unit, that comes under SIMD. MISD structure is only of theoretical interest and since no practical system has been constructed using this organization. So last is the most important, that is MIMD. MIMD organization refers to a computer system capable of processing several programs at the same time. So here we have multiprocessors, and they are working on multiple tasks, right? In SIMD, we know that there are many processing units, but they are working on the same task, right? And here we have multiple processing units, multiple processors, and working on multiple tasks. Okay, so that comes under this category MIMD. So multiple programs are being executed at the same time through the multiple processors. So multiple processors and multiple tasks, which come under this important category, that is MIMD. Okay. Next is Flint's classification depends on the distinction between the performance of the control unit and the data processing. So we basically have a control unit and data processing. So Flint's classification is depending upon the distinction between the two. So it emphasizes on the behavioral characteristics of computer system rather than its operational and structural interconnections. Okay, so it is working on behavioral characteristics, not on interconnection or you can say organizational and structural interconnections. Okay, so next is the introduction of pipelining. Okay, pipelining is a technique of decomposing a sequential process into sub operations. So we have to understand, here we have multiple segments and every segment is working on these sub operations. Okay, there is a big task which is further divided into sub tasks, and every segment is working on one of those sub tasks. Okay, so we have a big operation that is divided into sub operations, and we have multiple segments in a system, and every segment is working on the sub operation of that main operation. Okay, so that is the pipelining. And pipelining is again pipelining is a concept which is again there to improve the throughput of the system, to improve the computational speed of the system, right? So a pipeline can be visualized as a collection of processing segments through which binary information flows, right? So each segment performs partial processing. Why did it say partial processing? Because every segment is working on sub operation of the main operations. So therefore it is called partial processing, because it is working on the sub operation, okay, of the main operation. So the result obtained from the computation in each segment is transferred to the next segment in the pipeline. Okay, we have, I'll just show you with a figure that in a system, if we have 4 segments, one segment output will be the input of the next segment, right? So final result is obtained after the pass through all the segments. So we can say that the final result will be obtained after the processing done by the all segments present in the system. So a pipeline basically implies a flow of information analogous to an industrial assembly line. Okay, second last point, it is analogous to an industry's assembly line. You will just learn this through an example. Okay, so last is, it is the characteristics of pipeline that several computations can be in progress in distinct segments at the same time. Let's see this example. Here we have 4 segment pipeline, right? S1 is representing a segment 1, S2 is representing segment 2, S3 and S4, so on. Okay, these are all 4 segments, S1, S2, S3 and S4. Then we have R1, R2, R3 and R4. These are representing the registers. Okay, just see that output from the this S1, okay, going as an input to register 1, and through this register the output of the segment 1 is going to S2. Okay, similarly the output from S2 is going to R2, right? and from this register which stores the results from the segment S2 goes as an input to S3. Okay, so what we should understand from here, this S1 is a segment which is some part of hardware, and it is producing some output which is being stored in R1. Okay, from this R1, that means the S1, that the results which are produced by the segment S1 are being stored in R1, and from R1 those results are acting as an input for the segment 2. Similarly, segment 2 has processed the input which has received it from R1, and the results are stored in R2. Okay, and then R2 is giving those results as an input to segment 3, S3, and then S3 will process those results which are acting as an input to S3 and store the result of S3 in R3. Okay, and from R3 this goes to segment 4. Okay, similarly in segment 4 will process that, and then the final result, okay, will be stored in R4. So final result of the whole operation will be achieved in R4, through R4, right? Once the input has been processed by all the segments S1, S2, S3 and S4, finally we get the result in R4. And just notice one more point, that all the registers are connected by a clock for synchronization purpose, and at every clock pulse the data of R1 will be updated, right? Whatever the result S1 will produce will be stored in R1, let's suppose at clock pulse 1, and so on. Let's see further this with an example, then it will be better cleared. This is an example here. Suppose that we want to perform the combined multiply and operations with the stream of numbers A into B plus C. Let's suppose it's AI, BI plus CI. Okay, AI into BI plus CI. For I is equals to 1, 2, 3 up to 7. Okay, so what are we doing here? Here we are basically storing the content of register A into R1 and content of register B into R2. Okay, so this is the input we are doing to the registers R1 and R2. Or you can say, like I just said, it is registers A or B, or you can say these are the operand itself, these are the data itself, A or B. Okay, then we are multiplying the content of R1 and R2 and storing the result into R3. Okay, R1 multiply R2 and store the result into R3. That means what was there in R1? AI. What was there in R2? BI. Okay, then we are multiplying AI and BI and storing the result AI into BI into R3. Parallelly, what is happening when this operation was being done here? Parallelly, the CI input is being loaded into the register R4. Okay, and then we have R3 plus R4 in the next clock pulse, which is being stored in R5. Okay, add CI to the product. See, in R3 we have R1 into R2. That means we have AI into BI into R3. At the same time, we have received the input value CI in R4, and in the next clock pulse, we are what are we doing? We get this result AI into BI plus CI here, and that is being stored in R5. Okay, that means we are adding the CI with the AI into BI. So finally we get the result in R5, right? So see this highlighted point, R1 through R5 are the register that receive the new data with every clock pulse. Okay, this is what I was just explaining while showing that figure, in which all the registers are getting new values when it is getting a new clock pulse. On every new clock pulse, our registers are being updated. See, this is the same example. In this table, we have three segments shown: segment 1, segment 2 and segment 3. So we have three segments, segment 1, segment 2 and segment 3. On very first clock pulse, R1 and R2 are getting the values A1 and B1, okay, because the clock pulse is 1, right? So we have loaded this value A1 in R1 and B1 in R2. Now on the second clock pulse, what is happening? This segment 1 has passed this A1 and B1 this input to the segment 2. Okay, so now the segment 2, like we have just seen here, R3 is getting R1 and R2 on the next clock pulse. See this? So here on the next clock pulse, that is number 2, so A1 into B1 has appeared here in R3, okay, and at the same time R4 was being loaded with the value C1, right? But this is happening in the segment 2. R3 and R4 are the part of the segment 2, but here it is what is the segment 1 doing at the same time? It is loading the next values like A2 and B2 in the segment 1. So this is the point to be noted here, that this segment is not free. Segment 1 is not seated free at that point of time. These are taking the next data, A2 and B2, right? We have to go up to A7 and B7 because see this is, I was given here 1 to 7, right? So the segment was not idle. This was not free. It has loaded the next data, right? Now just see that on the third clock pulse, what is happening? We are getting this result in R5. What was R5 doing? R5 is doing R3 plus R4. R3 already has R1 and R2. Okay, so this is what we are getting in R5. A1 into B1 plus C1, right? So on the clock pulse number 3, we can observe that all the segments are busy. Okay, all the segments are busy on the clock pulse number 3. So that is our pipelining. All the segments are working all together simultaneously, you can say, and all are working on sub operations of one common operation. One common operation here was we have to do this calculation 7 times. Okay, then see the fourth clock pulse, we get the multiplication of this. Then on 5th we get A3 and B3 plus C3, and on 6th A4 B4 plus C4, and on 7 we have A5 B5 plus C5. Finally you get the A7 B7 plus C7 on the clock pulse number 9. So to do these 7 operations as we were supposed to do, we need total 9 clock pulses. Okay, so this is the benefit of pipelining. But if you see that if these segments will remain idle, it will take further more clock pulses. Okay, so in very less number of clock pulses, we are getting these 7 operations done. Okay, if these segments will not work parallelly, it will take further more clock pulses. Okay, so that is how we are speeding up the computational speed of the system by implementing this pipelining concept, right? Thank you very much. And this was all about introduction of the pipelining. However, we do have some numerical part in this particular topic that I will take in the next class. Thank you.